It is somewhat important whether we are working with real or complex vector spaces. Not immediately, but soon it will be. Okay, so I will so keep both possibilities in mind, and at some point you will have to distinguish between the two cases. Okay, I will tell you when. So we consider a linear map A hat from V to V. Then by choosing a basis, choose a basis, you get the associated matrix. You take dit A. This is independent of basis. So you can call this dit of A hat. And this has all the nice properties that you want. Okay. Now, so dit A is a function from linear maps. So dit A, so A mapping to dit A hat mapping to dit A hat is a function from the space of linear maps from V to V to R or C, depending on whether you are looking at real or complex vector spaces. Now, we are going to consider as associated function, which is related to dit A. We do this as follows. First, we do it for matrices, and then we, as before, one will do it for linear maps from a finite dimensional vector space. Okay, so for a while, let us consider M n cross n matrices, R or C. Okay, so we are not looking at linear maps from a vector space to itself. We are looking at linear maps from column vectors to column vectors, namely n by n matrices. And given, so let n be bigger than or equal to 1, given n by n matrix, we define its characteristic polynomial to be the function t going to TAT equals dit of TIN minus A. So, in other words, take a scalar T and send it to take T times the identity matrix minus A, that is a n by n matrix. So this is a n by n matrix. This is just the matrix with diagonal T, T, T. So if A is, this is just a matrix with entries Aij. So TIN minus A is the following matrix: T minus A11, A12, A1n, A21, T minus A22, and so on. I shouldn't forget these minus signs here, minus A31, etc. Okay, and then you take the determinant of that. Dit of this matrix is PAT. So as T varies, you get a function of the scalar T. So now but I have kind of cheated you. I have called this not the characteristic function of A. So by the way, this depends on A, so this should be called the characteristic polynomial of A. So this thing that I have written here unclearly, it's characteristic polynomial. So this is the characteristic polynomial of A. Thanks. Yeah. There was I. Yeah. So now, as I said, I've slightly cheated because I didn't call it the characteristic function of A. I called it the characteristic polynomial of A. So that means I'm anticipating that I will now convince you that it is not an arbitrary kind of function, but it's a polynomial function, and it's a polynomial function, so has a degree associated to it. So it's a polynomial function of degree n in T. So in other words, PAT has the following form. PAT A going to is a polynomial function of T of degree n, and this n is, remember, we are looking at n by n matrices. N is the size of the matrix. So if I look at 10 by 10 matrices, this function will be of degree 10. Okay. So, and in fact, PAT, the top coefficient, the coefficient of the top power is actually T to the n. And then the constant term is, so this will be T to the n plus A to the n minus 1 T plus T to the n minus 1 blah, 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 plus A0, okay? Why do I have a T here? So sorry, I was a bit garbled here, so let me write it again. So this is a this function of T, I'm going to prove in a minute, is not an arbitrary kind of function, but it's a polynomial function of degree n. More precisely, it is of this form. PAT starts off with T to the n. Then I have a term of degree n minus 1. So that will be of the form a n minus 1 T to the n minus 1 plus A to the n minus 2 T to the n minus 2, so on and so forth until you come to a constant A naught. So this is of this form. And remember, the way PAT is defined, it depends on A. So on the right-hand side, where could the dependence on A go? Because there is no dependence on A here or here, so or here. So the dependence on A is in the coefficients. So the coefficients of this polynomial depend on A. So let me repeat. Associated to every n by n matrix is a polynomial function of degree n of this form. It starts off the polynomial, the expression for the function starts off with the term T to the n. Then there is a term of degree n minus 1, some constant times T to the n minus 1, where that constant depends on which particular matrix you take. Then plus A n minus 2 to T to the n minus 2, where again the coefficient A n minus 2 depends on A. And then finally, there is a constant term of the polynomial, which there is no dependence on t at all. That is what I call A0, and that also depends on A. So this is my claim. So let me, because I have not proved this claim. This is a very, very important function in linear algebra. And once we are done with this, we will have defined very, very important functions of n by n matrices. Namely, these coefficients are very important functions. Sorry. These coefficients which depend on A are going to be very, very important functions. Okay. And we will have much to talk about. Well, let us understand these coefficients a little bit. So I have not yet proved this, but supposing this is true. Okay, this has been proved. What should A0 be?
So determinant of negative A?
Yeah. Yeah. So let us so as Shubham said, A0A is in fact determinant of minus A. And so since this is determinant of minus the identity times A, which is determinant of minus I times dit of A, and determinant of minus I is minus 1 to the power of n dit A. So the claim is that A0 is this. This is Shubham's answer. And let's justify that. Well, we know that PAT is t to the n plus a n minus 1 t a t to the n minus 1 plus A0A. So what is this? This is determinant of t I n minus A. Now take t equal to 0. So let us evaluate this function at t equal to 0. Then on the one hand, dit of minus A equals PA0. But if I put t equal to 0 in this polynomial, I get this is equal to A0A. So if my claim is true, this coefficient is minus 1 to the power of n times determinant of A. So that is a function of the matrix that you've already encountered, the determinant function. So the other coefficients generalize the determinant in a very, very important way. In particular, so just as determinant of A is invariant under similarity transformations, the other coefficients are also invariant, i.e. AL T inverse equal to ALA for any L between n minus 1 to 0 and for any invertible n by n t. Okay, I've told you a bunch of stuff about this polynomial, but I have not yet proved that the function is indeed a polynomial function. So let us do that. Just give me a minute, I'll be back. Yeah, sorry about that. Yeah, so let us get some intuition about this function. So, so to get some intuition about the function PAT, consider the special cases n equal to 1. So then P of A T equals, so A is 1 by 1 matrix A. So determinant of Ti1 minus A, which is determinant of T minus A, which is T minus A. Okay, so I mean, this is just a one everywhere. I'm just dealing with 1 by 1 matrices. So a 1 by 1 matrix is just a scalar enclosed in a square bracket. Okay, and determinant is that scalar itself. That's how we have defined it. So here, for n equal to 1, this is, so PAT is a polynomial of degree what? What is the degree of this polynomial?
1.
Of degree 1, because the top degree term in T is T to the 1. So it's a degree 1 and it has one root. It has one root. What is the root of this polynomial?
A.
A. Okay, so it's a degree 1 polynomial and it has one root. A. Now let's look at n equal to 2. So here A is of this form A11, A12, A21, A22, and PAT is T minus A11, T minus A22, minus A12, A22, which is T squared minus A11 plus A22 times T.
Minus A1 to A21, representing state.
Just once, like you take it. Thank you. Right. Minus A11, A21. Thank you. A12, A21. Okay. So what is my so remember my general expression was T squared plus A1 T. Sorry. A1 A T plus A0 A.
So plus
right?
A111, A22. You missed in previous equation.
Yes, thank you. Thank you so much. Yeah, otherwise I'll be in trouble. Yeah. Thank you so much. Plus A11, A22 minus A12, A21. Very good. So what is A1A? Remember, A1A is, this is the definition of A1A. A1A is the coefficient multiplying T in this expression. So what is A1 of A? For this case,
minus A22.
sorry,
Minus A11 minus A22.
very good. Is minus A11 minus A22. And A2A? Shakti, what is A2A?
So 1.
Sorry?
1.
Yeah, sorry. What is A0A?
So A11, A22 minus A12, A21.
A12, A21. And do you recognize this as something?
Yes, sir. Determinant of minus A.
Sorry?
Determinant of minus A.
Which is the same as?
And determinant of A.
Yeah. So this is determinant of A times minus 1 to the power of 2. So this is 1. Remember, I had said in general that this term is going to be determinant. So A0A is going to be minus 1 to the power of n times dit A. In this case, n is 2. So minus 1 to the power of n is 1. So which is why A0A is just determinant of A itself. Okay. Is this clear? Shakti?
Yes, sir.
Yeah. Okay. So now I had said that so A2A, of course, we know if the determinant is invariant if I multiply, if I do a similarity transformation. But now let us check A1 of A. I claimed earlier this fact in general. I said that all the coefficients are invariant under similarity transformation. So let us see, is A1 of A invariant under similarity transformation? In this example, I claim that this is true. Let's check. Let us check. i.e., A1 of T A T inverse is it equal to A1 of A? Okay, so see what that involves. That means, so what is A1 of A? Remember, just by inspection, A1 of A is minus of the sum of the diagonal elements of A, diagonal entries of A. Right? So this is A. And A1 of A is minus A11 plus A22, which is I take the diagonal entries and add them up, that is this, and put a minus. Okay. And what I have claimed is that all the coefficients of the invariant, so let's take a step back. What have we done so far? We have associated to every n by n matrix a function of a scalar t by this procedure. I have claimed without proof that this is not an arbitrary kind of function, but it is actually a polynomial function of exactly degree n. Moreover, the top degree term, the coefficient of the top degree term t to the n is actually 1. And if you believe this statement, we have checked that the coefficient of the constant coefficient is up to a sign, the determinant. The sign depends on whether n is odd or even. And now what we are, and I have also claimed that just like the determinant, the other coefficients are also, they are not arbitrary kinds of functions, but they are functions which are invariant under similarity transformations of the n by n matrix. Namely, if I take the matrix A and do a similarity transformation on this. By this, I mean, pick some arbitrary invertible matrix T, put it in front of A, and put the inverse of T on the right. I get a new matrix. These two matrices have the same values of all these coefficients, not just the determinant. That is what I have claimed. And now I want to check this claim for the case of 2 by 2 matrices, where we have identified the coefficient A1 as minus of the sum of the diagonal entries of the matrix. So the question is the sum of the diagonal entries of a matrix invariant under similarity transformation? So question. So this question is equivalent to, is the sum of the diagonal entries of a matrix invariant under of course, at the moment, we are only interested in 2 by 2 matrices because we are doing the example of 2 by 2 matrices. I can ask this in general. Okay. So, so let us in fact check that this is the case. Okay. Let A equals an n by n matrix, Aij, and let B equals Ta T inverse, where T is an invertible matrix. So Bij is TIL BLM T inverse LJ, sum over L M. So BII is sum over LM, TIL, DLM, T inverse Li. Sum over I equal to 1 to n, BII is sum over LM, sum over I, TIL, DLM, T inverse Li. Interchange the sums, sum over I, BLM, T inverse Li. This should be M here, M here, M here. MI, T,
So
IL.
it should be ALM, right?
Thank you, thank you, thank you, thank you, thank you. It's good to know that at least somebody is awake. BLSI. ALM, 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 ALM. Yeah, this is sigma LM, ALM. But this is just TI, this is just identity ML, which is sigma LM, ALM, delta ML. This is the Kronecker delta, which is sigma ALL, L equal to 1 to n. So in other words, sum of diagonal entries of B equals sum of diagonal entries of A. So my claim is actually satisfied for n equal to 2, because at least in n equal to 2, we have checked that A1 of A is the sum of the diagonal entries of A. So in fact, this will be the case for all n. The coefficient of A1 of A is the sum of the diagonal entries. This is A1, not A1, n minus 1. Okay. Yeah. We will see later that A n minus 1 A is minus 1 sum of diagonal entries of A. And there is a word for this, trace of A. So definition, trace of A or trace of A is the sum of diagonal entries of n by n matrix. Yeah. Okay, so now I have gone quite far without actually proving that this is a polynomial function. So how do we prove that?
Sir, I had a doubt.
Yeah.
Sir, could you scroll up a little?
Just 1 second.
Sir, what is the delta part? I didn't get the delta.
So I've been using this a few times. This is so thank you. Thank you for. So are you with me till here? T
Yes,
inverse T is the identity matrix. So this is the ML. This is the MLth entry of the identity matrix.
Yes,
Right?
sir.
So what do we know about that? That is equal to 1 if m equal to L and equal to 0 if m is not equal to L.
Yes, sir.
So you need a symbol to say that. That's called the Kronecker delta. So I could just leave it here. So let me not. So this.
Sir, I understand. I just didn't know what that
Yeah.
notation.
So
Now I
yeah.
understand.
Yeah. So this is called the Kronecker delta. So Kronecker delta symbol. Okay. This is called the Kronecker delta or Kronecker symbol. It's a very simple but useful symbol. That's all. It's a symbol that takes in two indices and is equal to 0 if both the indices are different, and equal to 1 if they are the same. Yeah. Okay, so now we actually need to prove the claim that.
So doesn't it follow by induction and the very first definition of determinant?
1 second. Is a function of the form PAT is t to the n plus an minus 1t plus a0. Okay. Keep making this stupid error. N minus 1 t to the n minus 1, etc. Yeah. So what was the question?
We can prove this directly by induction and the very first definition of determinant.
Which definition?
That inductive definition of determinant, writing that as a linear combination of determinant of degree n minus 1.
You mean expansion on the first column?
Yes.
Yeah.
Yes. Expansion.
Actually, that is what I wrote in my notes when I gave this last class last time. That will run into trouble. That it's not that. So you need to, you can possibly make it work, but then you need to have a more complicated induction. Because basically, if you look at if you expand on the minus of the first column, the matrices that you encounter are not of the form t to the identity minus something. The minors are not of that form. You just think about it. Yeah. So yeah, that strategy runs into problem. I'm sure you can make it work, but you will need a slightly more subtle induction. So I'm going to sort of do something that I think are, in fact, anyway, you are familiar with this. So proof prove by induction on n the complete expansion of the determinant namely given n by n matrix B, because I'm calling it B because we are going to apply it to not A. So yeah, dit B is sum over permutations sigma of signature of sigma B sigma 1 1 B sigma 2 2 B sigma n n. So these sigma all permutations of 1 to n. So I think most of you must be familiar with this. Are you familiar with this? Hello? Maybe you are not familiar with the notion of a signature. Srimati, are you familiar with this expression for the determinant?
No, sir.
No. Okay. So, so assume this for the moment. Actually, this, yeah. The important thing is that this is just plus minus 1. Okay. So, actually, that is enough for our purposes. So, if you don't know the signature of a permutation, prove by induction that did B equals sum over permutations of an expression where you have just plus minus 1, B sigma 1, 1, B sigma 2, 2, B sigma n 1. So this you can do. You understand this, right? So the claim is that the determinant is got of a n by n matrix is got by taking some element from the first row, some element from the second row, some element from the third row, some element from the fourth row, and some element from the nth row, like that. So this is B sigma 1, 1. This is B sigma 2, 2. So from the first column, you take the guy in the sigma 1th row. In the second column, you take the guy in the sigma 2th row. From the nth column, you take the guy from the sigma nth row. Multiply this with this. Multiply these with these, dot, 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 and finally end up with these. Then there is a similar, another permutation will give you something like this, ending somewhere. Take all these products and add them up and put in suitable sign, which is plus minus 1, depending on which sigma, what kind of sigma you take. It's not really important for our present purpose what that, whether that's plus 1 or minus 1. Okay, this thing you can prove by induction, starting from our definition of the determinant. Once you have that, take B equal to Ti minus A. Okay, so then what will happen is that dit of Ti minus A will be sum over over sigma minus plus minus 1 Ti minus A sigma 1, 1 Ti minus A sigma n 1. So now if sigma 1 is not equal to 1, so now look at any one of these, look at any one of these, okay? That will be of the form Ti minus A sigma j, j, okay? Now what are the possibilities here? Sigma j equal to j, in which case you will get T minus A j j. Sigma j not equal to j, in which case you will get minus 1 to the power of A sigma j j. Okay, so in any case, this will be each term in this sum. Each term in the sum is a product of n functions of t of the form either constant function of t or linear function of t. See, in this case, it's constant, and in this case is linear. See this. So look at each term in this sum. Each term is up to this sign a product of n functions of t. This is the first function of t. This is the second function of t, and there are n functions of t, and it's a product of n functions of t. And each of these factor functions is either linear or constant in t. So at most you'll have n linear terms in t. So if you take if all of them are linear of degree 1, then the product will give you t to the n, something of degree n. But in general, I'll get at least some of them will be of lower degree. So you'll get, so in other words, you don't need the full force of this expansion. You don't. So the full force of this expansion tells you that this guy, the sign is the signature of the permutation. If you don't know what the signature of the permutation is, it doesn't matter. All you need to know is that it's plus minus 1. That you can prove from my definition of the determinant in terms of expansion in columns. So the importance of, by the way, this also tells you how you should really think of this complete expansion of the determinant in terms of these paths. Take a guy from the first column, pick a guy from the second column, pick a guy from the third column, and so on, and then multiply these guys. That will give you one of these terms. Stick in a sign here that depends on how the guys are chosen. It's plus 1 if the corresponding signature has signature 1, and it's minus 1 if the corresponding permutation has signature minus 1. Now add up. Add up all these terms, and you get the expansion of the determinant. Yeah.
Two of the columns can't have same row, right? Like in the signature.
No, you can have the same.
I think that would be 0. Like those terms should be 0. Like from 2 column, if we pick same row on the same level while traversing that path.
Oh yeah, absolutely. Yeah. So it's a permutation. Yeah. You can't. Yeah. So you can't have a path like this. Thank you. Because it's a so see, the point is that this path must visit each row once. So you cannot miss out. The path as it goes up or down, it is visiting. So it starts from sigma 1, then it goes to sigma 2, it goes to sigma 3. So it can't visit the same row. So you can't have this. So thank you. So you can't have a path of this kind. Let me use a different color. Yeah, you can't have a path of this kind.
Sir, can I ask something?
Yeah.
Sir, if we prove that a determinant of ti minus a is equal to determinant of ti minus, small letter ti minus a similar transformation.
Just one second. Just one second. Hello. Actually, I will call you tomorrow. Yeah. So let's take a break now. I will stop the recording and I'll answer questions. 1 second.